Good morning, everyone, and welcome to Autodesk Virtual Academy, brought to you today by KETIV Technologies. I'm Nigel Umbayak, one of the customer success managers here at KETIV, and today I'm joined by my colleague, Nikhil Venkat. How's it going, Nikhil?
Good, Nigel. How are you doing?
I'm doing great. Nikhil is one of the application engineers here on the team, who one of his specialties actually is on the analysis side of things. So simulation, making sure that your designs are supposed to do what they're supposed to do and not fail. So, which is why, we've brought Nikhil on for numerous simulation webcasts, including this one today, where today we're going to be going over some validation of some results, right? So whether or not your simulation results make sense, what do they actually mean, things along those lines, specifically with a couple of thermal examples here today. Nikhil, do you have anything else to add there?
No, I think this is actually a follow-up on what we did previously, which was very basic in terms of, what is steady-state heat transfer versus transient heat transfer. Today we'll go one step further and we'll talk about analyzing, more advanced materials and also validating those results and making sure that your results are correct.
Absolutely, absolutely. So cool. Thanks again, everybody, for being here with us this morning or afternoon, depending on where you are in the world today. So with that, I'll go ahead and pass this over to Nikhil for the next 30 minutes or so. And like I said, if you have any questions, feel free to ask away. Thanks, Nikhil. Go for it.
Thank you, Nigel. All right. Thank you, everybody, for joining us. Now, as Nigel mentioned, talked about, today's going to be all about heat transfer and thermal simulation. So let's jump straight into it. There we go. All right. So, like I said, it's all about heat transfer today. And I would again refer you to the previous AVA for some of the more basic concepts of heat transfer. We will cover a couple of those today as well, but that talks about different types of analyses. So in today's outline, in today's AVA, we will go over, once again, conduction, convection, radiation. What is the difference between the three types of heat transfer? What is thermal conductivity? We'll talk about thermal conductivity because that's a big theme in what we're going to talk about today. And then we'll talk about the nonlinear heat transfer process. Most of the time, nonlinear heat transfer is not really considered, right? When you're doing a heat transfer analysis, you're applying a temperature and you're expecting, or you're applying some kind of thermal constraint, temperature, convection, coefficients, etc. And you're expecting a temperature profile at the end of it. But it's not always that simple, and there are certain materials, certain very commonly used materials as well, which require this little bit of advanced analysis. So we'll talk about that. We'll jump into Nastran, and after that, there will be a Q&A session. To start off, what is conduction? What is convection? What is radiation? Now, conduction is the transfer of heat between substances that are directly in contact with each other. Now, better the conductor, the more rapidly the heat is going to be transferred, and metal is a good conductor. Now, convection is a form of heat transfer which you'll see most likely in liquids and gases. Right? It's the most efficient way of heat transfer in liquids and gases. Convection occurs when you have warmer areas of a liquid or a gas that rise to cooler areas in the liquid or gas. Now, as this happens, cooler liquid will take the liquid or gas will take the place of the warmer areas, and this results in a continuous circulation, and you have that transfer of heat from warmer to cooler areas. You see conduction when you boil water in a pan, for example. Right? The bubbles of water that you see are the hotter parts of the water that are rising to cooler areas at the top of the pan. Now, radiation is a heat transfer mechanism where there's no actual physical contact between the two bodies. This refers to the movement of heat waves and does not need actual physical molecules to travel through. So again, we've talked about this before. High school problem: what is conduction, convection, radiation? The conduction is the actual the handle heating up. Convection would be the water boiling, and radiation is, of course, the actual heat source, the fire in this case. Now, conduction, specifically conduction, is, well, not specifically, but particularly conduction, is controlled by a certain quantity, which is a it's a characteristic of a material, and excuse me, and that is called thermal conductivity. Now, thermal conductivity simply defines the amount of heat that gets transported through a body, an object, as a result of a change in temperature. Now, usually this thermal conductivity is just thought of as being a number, right? So there are some certain, standard materials, things that you would commonly look at, commonly see heat transfer through. And as you would expect, vacuum has very, very, very little conductivity. So what that means is you don't see too much heat transfer. And that's kind of how, that's exactly how vacuum flasks work. Similarly, when you look higher up around this region with metals, right, you see that's fairly high. Diamond has the highest thermal conductivity. So this number that you look at, it's a good descriptor of how good your material is and how good your object is in transferring heat to its surroundings. Now, depending on the material and the mode of heat transfer, the actual applied temperature gradient can affect thermal conductivity itself. So the standard assumption is that thermal conductivity is a constant for a material, and if you have that number, you're good. But that's not always true. With metals, for instance, as the temperature keeps increasing, the amount of heat that it allows through it, or the amount of heat that it conducts, actually reduces. Right, so its conductivity reduces as the temperature keeps increasing. Now, I'm not sure how clear that is, but we're looking at glass wool, which is the bottom curve over there, cork, which is the next one, foam concrete, which is this one. You can see the conductivity is actually increasing, and asbestos conductivity is actually decreasing as the temperature increases. Or it's not decreasing, but it's actually steadying off, right? So as the temperature increases, you see a fairly steep rise, and then it just levels off at some point. Right? So metals actually have an inverse curve, and you're likely to see the conductivity of metals decrease as the temperature increases. Now, this is particularly seen in orthotropic materials, like wood or rolled materials. So if you're using sheet metal, it's likely that the standard conductivity value that you use, that one little number, is not really representing the entire behavior of the material over that temperature range. Now, orthotropic materials, what that refers to is when you have material properties that differ in three different directions, right? In three mutually perpendicular directions, those are called orthotropic materials. So for example, if you consider, let's say, a block of wood, you know that the wood will compress in the direction of the wood fibers, but it's not going to be able to compress or get tensed in any of the other directions, right? So you can apply a vertical load on wood, but you will not be able to similarly apply a horizontal load on that same surface, if that makes sense. Similarly with rolled materials, right? If you're looking at a sheet of metal, the properties across the thickness or the strength across the thickness is going to be less than the strength across the length of the sheet metal, right? So those are orthotropic materials. Now, if you're looking at a block of metal, for instance, that would be an isotropic material. So no matter what direction you're looking or what direction you're trying to measure the properties of the strength, the result is going to be the same. The behavior will be the same. Right? Now, there's, of course, certain materials like carbon fibers, which are anisotropic, which means that they don't actually have any, directionality. Now, why is this thermal conductivity important? How does the solver take into account, or how does Nastran take into account this change in conductivity? Now, the way it does that is through an iterative process, and there is a nonlinear process, right? What it does initially is assign the temperature to the model, so whatever initial temperature you've given it, it will assign that. Next, it will calculate the conductivity and radiation based on the initial temperature. So whatever's happening at that time gets calculated, and then eventually the next step will be to solve for the results from the first step become the inputs for the second step. And this keeps going until you get to the end of the process. Right? So it is an iterative process, and each iterative step is going to be dependent on the previous step. So that's how it takes into account all of the changes that you put in there. Now, we'll talk about this when we get into the software. You don't necessarily have to define the different conductivities at different time steps or at different temperatures. The solver will do that for you. Okay. Now, I know a lot of this is fairly, it's fairly theoretical, it's fairly abstract. Let's jump into the software and see what this actually, looks like, and what the workflow looks like for this. So I started off by talking about the types of materials as sheet metal specifically. So that's what I have here. I have a 10 by 10 sheet, to which I'm going to assign a rolled steel. Okay. First of all, what I will do is make sure to change the analysis type. So edit on that. And I'll use a nonlinear steady state heat transfer for this. Okay. But before we get to that, I mean, that's the objective. Before we get to that, I want to show you what a linear steady state heat transfer on this structure is going to look like. Okay. So what we want to see is at steady state, what is the temperature profile going to look like? I'll make sure I use SI for this. Oops. There we go. And for the material, I will go ahead and use there's a roll in here somewhere. Nope. Okay. Now, by the way, one of the things that I didn't mention previously is this is also how you would analyze heat transfer at areas that are going to be welded, right? So you're not actually going to be able to analyze the weld beads themselves, but you will be able to analyze, excuse me, the temperature profiles of the two materials being welded. So if you want to look at what that temperature profile looks like, you would need to do a nonlinear heat transfer. Okay. Now notice, as soon as we select a linear heat transfer type problem, the thermal part of the material properties get active. And this here is the thermal conductivity that we're interested in, right? This is what we were talking about. We're using for this an isotropic material model because we're not interested in the strength, we're only interested in the thermal properties of this. Okay. Now we don't need any constraints. I will apply a convection load on that edge, an ambient temperature of 293 Kelvin, which is 25 degrees Celsius, and a convection coefficient of 2.93 10 to the minus 3. Okay. Notice there is no temperature dependence or time dependence on the convection coefficient and the ambient temperature. That's because we're only looking at a linear steady state heat transfer. We're not looking at what happens as a result of the change of time. Okay. I'll also apply just a direct temperature load. Actually, let's just apply body temperature. Okay. So we will apply a temperature load on just that specific edge of 315 Kelvin. Okay, there you go. That's a glyph for the temperature load. Now we'll go ahead and mesh this. Now remember, with a thermal problem, you always want to be using linear order meshes. I know that, you know, in general, a parabolic mesh is a good general purpose mesh, right? You can use a general purpose element. It's good for most types of problems, especially structural problems. But when you're running a thermal analysis, make sure you're using linear element order. I use an element size of 6 millimeters. Create a mesh. Okay. And there we go. We have two loads in there. I can go ahead and solve this problem. Okay. So there we go. We see that we have an actual temperature profile here, and it's giving us the maximum temperature on. It's telling us the maximum temperature on that end is 315 Kelvin, and that never actually, you know, loses heat. And the lowest temperature is actually pretty small, so because the convection coefficient is fairly small. Okay. Now, didn't mean to do that. Now, what if I were to change this to a nonlinear problem? Right. So let's do a nonlinear steady-state heat transfer. And in here, what we want to do is define. Notice how the thermal conductivity temperature dependence is actually active. Right, so we can set up a temperature dependence for this. And what we're saying is, no matter what the, or rather what we're saying is, depending on the temperature, as the temperature changes, the thermal conductivity, the amount of heat that passes through at that temperature, is also going to change. Right? And so you won't see that, or you're not likely to see that uniform distribution of temperature. The temperature is now going to look slightly different. So we'll go temperature in Kelvin. So let's say 0 degrees, 25 degrees to 93, 20 degrees rather. 14.9. And you can pull up this information online. There's a lot of empirical information out there, but your vendor, your material vendor, should also be able to give you this information. Okay. So I'll do 293, 343 is 6. 16.4. $360. There's a jump at 360. It's 17.8. And at 400, it's 19.3. Okay. Now here we have defined this distribution. You can look at a plot of this as well. And you can see how the temperature actually increases, or rather the thermal conductivity increases with an increase in temperature. Thermal conductivity is in most places you will see it defined as lambda, the Greek letter lambda. Nastran defines it as K, represented by K. So now you have this table 1, I'll hit OK, and that's now active. I don't know if you can see it, but there's actually a red check mark above the curve there. Okay. The rest of it is pretty much the same. We don't have to make any changes in here. You can, if you like, add a temperature dependence to the convection coefficient now, since it is a nonlinear problem. But I'm going to leave it blank. There is no. We're going to use a standard constant convection coefficient. Oops. Oh. That's another thing with a nonlinear problem. That's one thing I forgot to define. You do have to set up an initial condition, right? It doesn't know where to begin from, so you have to set up an initial condition. So go into the loads and say initial condition. The only one available for this problem is temperature, and notice you're not allowed to select any entities, right? That's because this is a global setting. It applies it to the entire assembly part, whatever you have there, and it's just meant to define, the ambient temperature, the initial temperature that you're starting the analysis off at. So I'll say the initial temperature is going to be 290, 17 degrees Celsius. Now, if you go ahead and run this, you'll actually see that it's trying to converge, and you'll see the different time steps it's running in. Give it a few minutes. There you go. Okay. So what we're seeing here is actually fairly interesting. So it applied it in one time step. You can define how many time steps it uses. But if I turn off the visibility of all of this and make this a little prettier, there you go. So you're actually seeing that the minimum temperature, the 315, since the convection coefficient, or the thermal conductivity is lower at that temperature, you're actually seeing that this area is at the lower end of temperature, right? Because that's the applied 315 degree Kelvin. The rest of it is actually conducting more, and the temperature is increasing. This is what you're likely to see with a sheet like this, right? You're actually likely to see more transmission of heat. Now, some of these numbers are exaggerated, of course, but you're likely to see transmission of heat and greater dissipation of heat further away from the point of application. Now, if you were to do a transient heat transfer analysis here, you can actually look at the temperature distribution as a function of time. So after whatever X number of seconds, you can see what the temperature is. Are there any questions at this point? I'll just give you a minute to fill in all your questions while I jump into the next model that I had here.
No worries. And Nikhil, while you're jumping over there,
Mm-hmm.
we have a question from YouTube. There is a user asking, where do you get the number for the convection coefficient?
Oh, that was just a number, an input that I had available to me. So the convection coefficient, if you're talking about where you would get it in reality, there is a bit of math that you need to do to get that number as is. So yeah, we can definitely talk about that offline. I'm sorry. But yeah, there is a bit of math that you need to do to get to that number based on your ambient temperature and just the basic convection, convection parameters surrounding the system. Okay, so the next thing that I want to talk about, and this is just a follow-up from what we did here. We defined with the sheet, what the conductivity was going to be as it changed as the temperature changed, right? We defined that variation. We defined the XY plot there. Now in this next one, we're actually going to allow the software to do that. Right? Some of you may have seen this model before. This is one of your tutorial files, by the way. So you will be able to find this in the tutorials, in the Nastran tutorials. So once again, we're going to go ahead and change this to a nonlinear steady-state heat transfer problem. The material we're using is steel AISI 4130. Right? Again, thermal is active, but this time we're not adding any temperature dependence, right? We're allowing the solver to calculate what that thermal conductivity is going to be at each temperature. Okay. Again, I'm going to use a linear mesh for this. Use a mesh size of 0.09. Again, these are numbers that I have. Normally, you would have to do a little bit of trial and error with the mesh to get it right. But this is a pretty fine mesh that we're going to create. Just making one of the completes. And this manifold, by the way, it's in the C users public documents folder. So if I'm sure you could just Google this and it'll point you to where that is. But yes, you can find this and a whole bunch of other models, tutorial files in that same location. Okay, there we go. Now, the way you know, by the way, that it's a linear mesh without actually opening the mesh settings, if you look on the left here in the Nastran model tree, you'll see that the number of nodes is significantly smaller than the number of elements. That's when you know that it's a linear mesh. Okay. Now, the way this problem is set up, there's a whole number of surfaces, and that's how this manifold is modeled, right? So each tube here is split up into a whole number of surfaces. So I actually have the load set up already. So there's a heat flux load that will add to this. There's a convection load that will add to this, and an initial temperature as well. Okay, and I'll open up those loads and show you exactly what they mean. Just 1 second. And here it's basically just creating that file in the background that it uses to solve the problem. It does hang up on this sometimes. And again, part of this has to do with the fact that our mesh is so fine, right? Okay, so I don't want to just sit here while this finishes. Instead, I do have one with the results in here already. So I'll go back, explain the different loads. So we have a heat flux load, which, wait a second, that is applied to the internal surfaces of the tubes there. And the heat flux, we have a small magnitude here, it's not very large. Next, there's a convection load. So again, that convection coefficient, we can talk about how to get to that one single number. But again, typically, even with the convection coefficient, you're likely to see a temperature dependence, right? So it's not always that you have one single number, but yes, we can talk about that. So again, the convection coefficient is pretty small in this case, and BTU is British thermal units. This is not in the same units as previous, by the way. And then there's also an initial temperature of, I believe, 70 degrees Fahrenheit. Yep, 70 degrees Fahrenheit. And again, it's the same sort of initial temperature that gets applied globally. So again, the way this problem is set up, the solver is going to calculate what that thermal conductivity number is going to look like at each time step, at each temperature step. Okay. If I jump into the results, and this is one that I had solved previously, and yeah, so this is one that I solved previously, and I have everything set up in here. So you see now, at the end of this, at steady state, which is basically equilibrium with the atmosphere or with the surroundings, at steady state, you see that the tubes, actually, the maximum temperature is somewhere in here, somewhere within those tubes. And this is a result of, calculation of the solver actually calculating the thermal conductivity. So you see that there's a much better temperature dependence in here, a much more uniform temperature profile that that we see here. Now, keep in mind, you cannot use the results from a nonlinear steady-state heat transfer to run a nonlinear stress analysis, right? You can do a linear static from here, but you cannot do a nonlinear stress analysis. So keep that in mind. But yes, this is actually a much more accurate temperature profile than you would have gotten if we had just done a linear heat transfer in this case. Any questions here?
Don't see any right now, Nikhil. I'll pause you if there are some, though.
Okay. So that's about all I had in terms of the software. Now, quick note before we break for Q&A. Next week, there is a streamlined productivity training coming up, which is it's going to incorporate some of this material and some of the previous material that we had covered. So it's going to go deep dive, 4-hour training session into thermal simulation in Inventor Nastran. Now, this is part of our streamlined productivity sessions. So every month we have 4-hour training sessions on advanced workflows, right? And this is specific to our streamlined customers. Usually, but we're allowing anyone to jump in and sign up for a free trial of Streamline using that link at the bottom there. So we cover AutoCAD, Inventor, CAM software, Vault, Nastran, a whole gamut of products and software that you can use to just refresh some of your processes, refresh some of your workflows, or even just jump in for something very specific like the thermal simulation in here. So I'm hoping to see a lot of you there, and please feel go ahead and sign up for that. So that's going to be on September 18th at 8:30 Pacific. So hopefully you can join us then.
Absolutely. I know I will be in there. Even though I work here, I sit in the classes because learning stuff is awesome. And I'm really excited to see what Nikhil's got the show for Inventor Nastran Thermal next week. So I'm really excited for that, Nikhil. I've seen some of the stuff you've put together. It's looking real exciting. So.
And Nigel, correct me if I'm wrong, but these sessions are not recorded, right?
Which sessions?
The Streamline productivity training sessions?
The productivity training session is recorded and available to people on Streamline. So if you have Streamline, you can't make it, I have it for you. But I am not available to give the recording out to people who are not some KETIV Streamline members. So keep that in mind. If you want it and you're not KETIV Streamline, email me. I'll see if I can pull some strings. I'll see if there's something I can do for you. But yeah, generally I'm not allowed to give the recordings for the productivity training sessions to people who are not on Streamline. But if you want to see it, go ahead and give me a ring. I'm more than happy to see what I can do. But with that, I think that's everything that we had for questions today. Again, Nikhil, thanks for joining us this morning. And we'll talk to everybody next week for our special ANSYS Discovery Live and Inventor Workflow AVA. So thanks again, Nikhil, and everybody. We'll see you next week. Bye-bye.
Thank you all.